Hi everyone, welcome to the first video in Unit 3, Intro to Extrema, Part 1. Here are the objectives. We're going to be reviewing several concepts. We're going to define extrema and we're going to go over the extreme value theorem, which we need all of the previous information of these objectives to get to the extreme value theorem. So stick with me. This is a fairly lengthy video, but I promise you we're going to use these concepts. So this screen pretty much gives you a review of interval versus set notation. And most of this you have seen before. It gives a pretty good example of what we were talking about here. Set notation you're pretty familiar with. This is D means domain. This means the set of all x such that x is greater than or equal to 1. And you could see the brackets that they use for that. And then over here in interval notation, same domain. This says the same thing, the bracket. Include the 1, comma, to positive infinity. And remember, it's like a number line. So you start at the smaller and go towards the larger. The only thing that I would disagree with on here is that they're using a bracket for infinity. And we don't usually use a bracket in set notation for around infinity. We use parentheses on both sides, so I've corrected those. This is how you would write it in set notation for all real numbers, the x value for all real numbers, and this is how you write it in interval notation. And then you have quadratic and for the ranges in the same basic thing. Now this one would be a bracket, this one is not. So on here we're going to write each of the following using set notation, interval notation, and as a graph. So for instance, number 1 is in set notation because it says x is less than or equal to 8. So in interval notation, we're going to start off, we know that we're going less than 8, so 8 will be here. We're going to go from negative infinity to 8, and we're going to include 8 because they're of the equal sign. So that's how you would do it in interval notation. As a graph, here's 8. We would include 8 and go everything to the left. All right. Number 2 is already in interval notation. It says that as x approaches 2, right, it says go from negative infinity to 2, include 2, then jump up, don't include 4, and go to infinity. So this time I'm going to start with the graph. So here's my graph, and here's 2, and here's 4. And on here I'm going to include 2 and go this way. But on 4, I'm not going to include 4. And there's a couple ways you could do that. You could do an open circle, which I prefer. Or I've seen some of them where they actually put like a parenthesis here and a bracket there, which means about the same thing. All right, so set notation then, if you're going to do that, you would say that x was less than or equal to 2. And x is greater than 4, but not equal to. So that's how that works. Now, here's another really important concept that we need in calculus, and that's the idea of an open and a closed interval. Oftentimes you can have a maximum value or a minimum value that's different depending on whether you have an open interval or a closed interval. So as we're looking here at this first example, we see that this is a closed interval from -1 to 2. So that means that there are closed circles on this parabola. This is still a parabola, right? It's x squared plus 1. Here's the parabola. And because this is closed, the lowest point here is here, but the highest point is one of the endpoints. Okay? The difference here is that it doesn't include the endpoints. So on this is the same graph. It's the same interval. It's just a open interval because this is not closed. So this is not a maximum because it doesn't exist there. This is, however, still a minimum. Okay, here you can see that you have a discontinuous, right? There is a point there, it's just not where the circle is, and then it is a closed interval. So here you would look at this is not a minimum. This is also not a minimum because it's not the lowest point and it's an endpoint. And then this is a maximum point, and this is a maximum because it exists and it's closed. So extrema, maximums and minimums, can occur at interior points or on the endpoints of the interval if they exist. Extrema that occur at the endpoints are called endpoint extrema, which, wow, I bet you could have guessed that. So on this particular screen, what we're going to do here is we're going to analyze this polynomial graph that we have over here. You can see it here, a polynomial graph. And we're going to identify the following intervals. Now, you're going to have an exercise in class when you do this. So let's talk a little bit about all parts of this thing here. So this is a polynomial with two terms. So it is an x to the third, a third degree polynomial. It goes up, the end behavior, it goes up to the left and down to the right, so that would be an odd function. It has 1, 2, 3 real zeros because it crosses the x-axis 3 different places. In fact, we know it's at -2, at 0, and at 1. Okay? We also know that this is an open interval. So this open interval means that there could be a minimum, all right? So as we move left to right, we see that this graph is decreasing to a minimum, increasing to a maximum, and then decreasing after that. Now, these are not the highest points on the whole graph, so these are called local minimums, relative minimum and max. If they were at an endpoint or they were actually the highest point of the graph, then they would be absolute or global. Okay? So we'll use those words again. All right, so, and you can see here that this is like a soup bowl up. So this is concave up, this is concave down, and in here somewhere is where they change from concave up to concave down, and that would be an inflection, a point of inflection. Changing from one to the other concavity is an inflection. All right? So we've answered a lot of these, so let's go ahead and see if we can figure them out. What are the intervals of increasing? Well, increasing is from about here to here, right? So we would have to guess just a wee bit on this particular graph. This isn't a great graph, but increasing would be from about -1 to, I don't know, 0.7. And then decreasing would be from -infinity to about -1, right? And then again from about 0.7 to infinity. Now notice I didn't get too bent out of shape, that I had to guess a little bit there. On some of the other graphs you'll be able to tell as well. Your concave up to concave down, right, would be from -infinity to the point of inflection, which seems like it's at about -0.4. All right, so the point of inflection is at -0.4. There's a max at here, here and here. And so we could notice that it's also their maxes and the mins are going to be where the intervals were for increasing and decreasing. So there's a max at 0.7, x is 0.7, and then there's a minimum at x is about -1. Okay, the leading coefficient is negative. The end behavior is odd because it goes like that. All right, so all of those things can be found using here. It'd be nice if we had a lovely little neat graph, but we don't. So we're going to do a lot more of this in class. We would talk about the domain. The domain of this function is all reals. In interval notation looks like this. Okay, it's got 3 zeros at -2. We've done all of that. So this diagram, I just wanted to remind you what it looks like in notation and also in the graph when a function is increasing or decreasing. One of the huge things that we have to know about this unit is we have to be able to read the notation and understand what it means when it says if f prime of c is less than 0. Well, if f prime of c, if the derivative is negative, right, then f of a is greater than f of b, which means that the function is decreasing. All right, so if I'm looking here, I see that the derivative, this is actually number 1 right here, right, because the function f of a is greater than f of b. Also, the slope is negative, okay? So then on number 2, it says that the slope is positive. So I'm looking here, this is the slope is positive. You'll notice that this time f of b is greater than f of a, right? You can see that the flip sign. So this means that the function is increasing. Of course, this last one, I have here's a, here's b. It says that f prime of c is 0. So it's a horizontal line. So that means that it is going to be constant over this line. So this is 1, this is 2, and this is 3. Here's another review, the review of continuity. All right, continuity in its most basic thing says that a point, if a function is continuous, then every point exists right next to the next one. So in a very simplistic way, we would say things are continuous if I could draw along my pencil and not have to pick it up. But that's not really a good definition of continuity. So here was our definition of continuity. We said that, first of all, f of c has to exist. So there can't be any holes in this graph. F of c has to exist. So for instance, even here, does f of 3 exist? Well, yes, it does. It's down here. So even this diagram, which is obviously not continuous, fulfills definition part 1 because there are no holes. And I know I can hear you. The silence is deafening. This is not a hole. This is defined here. It just is not defined right there. Okay, so the second says that the limit as x approaches c exists everywhere. Well, we remember the definition of a limit. To have a limit, it has to be the same limit from the left as it is from the right. So we see here on this particular function, and right here, it fails at 2. It failed nowhere on number 1, but it does fail on 2. It fails right here. Because here, the limit from this side is the same as the limit from this side, even though the point is defined down here. So this actually fulfills these two rules of continuity. So 1 by itself does not determine a continuous function, and 2 is not going to even determine a continuous function. It requires all 3 parts. It says that if the limit, so we've already eliminated this part right here with number 2. We've eliminated nothing with number 1. But number 3 says those two values have to be the same. So here I look, here's the limit as it approaches here. The limit as it approaches 3 is 0. But what was f of 3? -1. So because these two things do not exist, this is not a continuous function. So here, to blow your mind a little further, what if I just wanted to go from here to here? Is that a continuous function? Well, does f of c exist all over that domain? From here to here? Why, yes, it does, including the endpoints, right? Does the limit exist everywhere here? Yes, it does. Is the limit the same as the f of c for the over this entire interval? Yes. So even though this is discontinuous right here and this is discontinuous, from here to here it is continuous. So you can set up an interval anywhere on the function. Like I could do another one over here and that would be continuous. So it's continuity over an interval would exist on this function versus continuity over a domain. So this is not continuous over its whole domain, but it is continuous on an interval. This is a huge concept, and I hope that you have a better understanding of it. So the intermediate value theorem we have gone over before. We've done a little bit with it, but we're going to take it even further and we're going to build on it, especially when we get to Rolle's theorem and the mean value theorem. But the intermediate value theorem, remember, says that if f is continuous over the interval, which from here is from a to b, if it's continuous over this interval, and n is any number between f of a and f of b, where f of a doesn't equal f of b. They have to be different. Now, this one doesn't have to be bigger, but they do have to be different. Then there is some number c in the interval such that f of c equals n. So where we used this before, another way of saying this is a continuous function cannot skip values. And that, if you think about it, what a continuous function is, yes, of course not, it can't, right? It cannot do that. Otherwise, it wouldn't be continuous. So a continuous function, right, if it gets from one value to the next and it's continuous, somewhere in this interval, it's got to cross this n value. And that's what that is. Now, sometimes they use it to determine if there's a zero there, right? Because if you have an f of a that's above the x-axis, and you have an f of b that's below, then somewhere in between there it's got to cross. That's the intermediate value theorem. It's saying that if it's continuous, then there is some value. So a continuous function cannot skip values. And if you read this, which I hope you did, it said it could do that possibly more than once, right? Because who knows what it's doing between a and b. It could go up and down, cross it 3 or 4 times. Okay, so I mentioned this in the introduction, but the definition of extrema are that they are the maximums and minimums over an interval in a function. Now that interval could be the entire domain, or it could be a closed interval, or it could be an open interval. And so what we have here, we have absolute or globals. An absolute is the highest point on the graph. This is a local and a global. So in other words, they're all local, but a few of them are absolute. Okay? And to me, local sounds like global. It's easy to get those two mixed up. But relative and absolute actually seem to me to be more descriptive. But I want you to have the whole vocabulary because your book and the AP exam and everything else, they use them interchangeably, and I don't want you to be at a disadvantage. So looking here, notice that this is a maximum, but it's not as high as this maximum. This is the absolute maximum over the entire, this domain that we see, over this interval that we see. This is a local minimum. It's not the lowest. This part goes lower. Okay, so let f be defined on an interval I containing c. F of c is the minimum when f of c is less than or equal to f of x for all x in I. And f of c is the maximum when f of c, the y value, is greater than or equal to f of x, all the y values for all x. So that would be a max. So all maxes and mins are relative or local, but a few of them are absolute or global, and it depends on the interval. So I wanted you to look at this one really quick because this is a closed interval. See the endpoints, it doesn't have arrows. So this is an endpoint, right? And it's lower than some of the other points, so it's a local min. On this other endpoint, notice that it's lower than all, so it's another local min, right? This is a maximum point. You can see it changes from increasing to decreasing, the local max. It's not the highest point. This goes from decreasing to increasing, a local min. Increasing to decreasing. Now, this point right here is not differentiable because the limit from the left is not the same as the limit from the right. The slopes are different on either side. It's called a cusp. So this is an extreme value, but it is not differentiable. Okay? This is a global min. It's the lowest point in this interval, global min. This is not an extreme value because it's not changing, and also it's what we call a corner. And so the corner is not an extreme value. Here's a global max, the tallest max, and it almost looks like it's another one of these cusps, and then a local min. Same deal here. This is a max, this is a local max, this is a local min, and this is not an extreme value, it's a corner. Okay. The extreme value theorem. I told you there would be quite a few theorems here, and we've revisited the intermediate value theorem, but this is the extreme value theorem. It says if f is a continuous function, we had to review continuity, continuous function on a closed interval, then f has both an absolute max and an absolute min for some numbers c and d on that interval. All right, so f has to be continuous. It has to be a closed interval, right? So here's my closed interval from a to b. Here is a function that looks like this, and it has a maximum absolute here and a minimum here. And this is a minimum absolute because it is lower than the endpoints. Okay, so these extrema can be interior or they can be on the endpoints. So on this one, you see we have a continuous function. This one, the highest point is the endpoint, right? This is a maximum, global max. This is a global min on that interval. Okay, here's another one, right? Here's another one where I start off. Here's the global max, global min. And then on this one, because I always think, well, okay, that's awesome. It assumes that it's moving, right? What if this one doesn't move? Well, think about it. A constant function, every single point is both a max and a min. So on the extreme value theorem, it didn't say that f of a had to be different than f of b. That was the IVT. This one just says it has to be a continuous function, and it is. Okay? So it says if it's a closed interval and it's continuous, there has to be a max and a min. And there is. So on this last thing, I want you to think about, and go ahead and write, you could probably copy this pretty easily onto your paper. See if you can determine whether each labeled point is an absolute max or min, a relative max or min, or none. Okay? So draw yourself a little one of these and see if you can figure out which is which. So A, B, C, D, E, F, and G. And determine if it is a max or a min, and then what kind, relative or global. Okay? And then I will see you in class.